Okay, so we need to discuss sampling distribution as different from normal distribution and standard normal distribution. We've talked about normal distribution, we talked about standard normal distribution. Now let's talk about a sampling distribution. Now, if you repeatedly take samples from one or more populations, so you can't study everybody. Remember, one of the examples in the previous class I gave was about studying the blood pressure, systolic blood pressure, and the diastolic blood pressure of about 1 billion people. Beautiful. But we don't always have the luxury of time, money, expertise to study that large group of people. So let's assume that we are taking samples from the population, adult population, and we want to study their systolic and diastolic blood pressure and see whether we can make any judgments as to what is normal, what is abnormal, and so on and so forth. So when you take samples repeatedly. So for example, I can sample a class of 1,000 people. I can collect a sample of 100 from 1,000 in an infinite number of ways. And no two samples will be exactly the same. If I take 100 people out of 1,000, I can do so in an infinite number of ways, and no two samples will be identical. There will be similarities, but they will also have differences. All right. So this is the illustration of what I was talking about. This is the population. Mu is 3, so the mean in this population is 3. The mean value of this population is 3. And we've taken 1, 2, 3, 4, 5, 6, 7, 8, 9 samples from this population that has a mean of 3. Now, each of these samples will have a mean that is different, maybe the same, maybe different from the population mean. So that's why you're seeing X bar. X bar is sample mean, mu is population mean, if you remember. So I can collect samples of 4 persons from this population in, at least I've shown 9 different ways here. It's possible to do it in 20-something different ways or 30-something different ways. What if I was to plot the frequency of each of these different samples? Using their mean and standard deviations. Using their mean and standard deviations, I was to plot a frequency table, a frequency graph of all these different samples using their mean. What I'm using to plot it is their mean and standard deviation. Their mean and standard deviation. If you see that, for example, let's look at the mean. You see in here, mean is 3, 2, 4, 3, 1, 4, 3, 5, 2. Very different. Similar, different. Now, how did I get this graph? Is to say I'm plotting the mean versus the number of times of occurrence of that mean. Let's look at it. 1. Frequency of occurrence of 1 is once. 1. Let's look at all of this, all of the samples. Mean occurs once. Frequency of 2. 2 occurs twice. There's a 2 here, there's a 2 here. Frequency of 3 occurs 3 times. You see 1, 2, 3. And so on and so forth. 4 occurs 2 times. 1 here. Where's the second 4? 2. While 5 occurs once. Mean of 5 occurs once. So the number of times the mean occurs from the different samples becomes your frequency, and then the mean values are there too. So you have a y and an x axis. Now you know that it is very easy for me to now plot a normal distribution curve. To plot a curve around this, as you can see, it's possible. So that brings us to the central limit theory. And it's really, really important for understanding inferential statistics that we understand the central limit theory. What it says is that the sampling distribution of certain statistics will approach normality as the sample size increases, irrespective of the shape of the sample population. Remember that all the while I've been talking about the normal distribution curve, I was talking about biological variables, that biological variables of themselves tend to assume a normal distribution pattern. And that 95% of the values of a biological variable will lie between minus 1.96 and 1.96 standard deviation of the mean from the mean, while 99% will run between minus 2.58 and plus 2.58 standard deviations from the mean. Fantastic. This, however, is not often applicable to studies that are measuring other types of characteristics that may not really follow the normal population curve. I'll give normal distribution curve. An example is age. Age. If I want to measure the mean age of your class, I can bet you your class is how many? Is about maybe, I don't know, 8, maybe 10 max. I can bet you that it will not follow the normal distribution curve. I can bet you that you cannot plot any curve with the mean ages of members of your class. It would not make much sense. It will not. However, if there, for example, the population is about 100 people, and I collect sample age, mean age, and I'm able to have 20 different samples or 30 different samples, let's assume 30 different samples of age, 10, 10, 10, 10, 10, 10, 10 in each of the sample of 100 people, and I get the mean age of each of these 30 samples, and I plot it on a normal distribution curve, it will follow and obey the laws of normal distribution. But that is what it means by saying approach normality. The simple way to say it is that as the sample size increases, the sampling distribution approaches normality. The sampling distribution approaches that of a normal distribution curve. This is the reason why your research, your sample size must be high. Your research needs to be sufficiently powered, is the word we use, and I will explain what that means later. So that even if the variable you're studying by itself is not amenable to the normal distribution curve, your sampling, if the sample size is high enough, your sampling will help to ensure that the distribution, your sampling distribution for that particular characteristic will approach normality. And that is the basis of what we are going to talk about next. So standard normal distribution and central limit theory are two of the cardinal things that underpin the whole probability principles that shape and guide our bridge between descriptive statistics and inferential statistics. Again, I pause for questions. So we are now in we were saying everything we're saying, and everything we're discussing. Come to this inferential statistics bit that looks at hypothesis testing and confidence interval estimation. All right, so let's understand inferential statistics a little bit. When we talk about inferential statistics, we're talking about techniques used to provide information about parameter values based on observation made on the values of statistics. I've said this so many times. When you are measuring and doing statistics within a sample, you are using statistics. So the summary measurements are called statistics within a sample, while the summary measurements are called parameters within a population. So to be able to use a sample to make inference about what will be happening in a population, you need inferential statistics. And there are two broad areas of statistical inference. One is hypothesis testing and estimation, and two is confidence interval estimation. One is hypothesis testing, and two is confidence interval estimation. And we'll look at both of them. Now, in hypothesis testing, you want to have a specific statement or a hypothesis. A hypothesis is a calculated scientific guess about the relationship between sample and population, or the relationship between two samples. So you generate a hypothesis about the population parameter and the sample statistics. And you want to use that hypothesis to assess the likelihood, probability again, the likelihood that your hypothesis is true. So there's a test that you will do. There's a statistical test, inferential statistical test that you will do. And there are different kinds of tests based on the variable that you are dealing with, and how that variable, the variable you are dealing with, and the characteristic of the sample that you are studying. There are various kinds of tests that you will do, and we'll go to what those tests are. But a hypothesis testing, basically, you want to make a statement, a guess about the likelihood, and you want to test to see whether that hypothesis is true. What's the likelihood that your hypothesis is true? But that your guess is about the relationship between sample information, sample summary information and population parameters. So sample statistics and population parameters. In confidence interval estimation, you use sample statistics to generate estimates about unknown population parameters. We are estimating that. If I'm seeing the mean value as this in the sample, the mean value in the population is likely to be between this and this. That is what confidence interval estimation is. It's not the likelihood that your hypothesis is correct or not. No, it goes a step further to say, if this is the value in the sample, then I can actually calculate what is likely to be the value in the population. It will be between this value or that value. I can't be certain to say it is this exact value, but I can come up with a range. It's an estimate range of which I have confidence that the population value is between this and this. We'll look at it. So we've talked about hypothesis testing. We've talked about confidence interval estimation. There's another slant to confidence interval estimation, and that's a sample size estimation. But we'll look at sample size more in detail when we look at research methodology. I'll talk about the different sample size formulae and how why, when we use what and why we use them, and so on and so forth. But just let us just make progress. So we'll be focusing on hypothesis testing and confidence interval estimation. We will not look at sample size in this class. All right. Remember what I said, that the probability theory and the central limit theory are what underpins your ability to carry out inferential statistics. So your probability theory talks about the likelihood of occurrence of an event, and it is the relative frequency probability theory that we use that helps us develop a normal distribution curve that says that 95% of the values of a variable in a population, where that variable is normally distributed or follows a normal distribution pattern, 95% of the values will lie between minus 1.96 and plus 1.96 standard deviations from the mean. And that even if you have a variable whose values are not normally distributed, if you have a large enough sample size, if you are able to take enough samples, if you have a large enough sample size, central limit theory says that the characteristics of that sample will mimic a normal distribution curve, even if the variable normally will not normally distributed. As you have a large sample size, the larger your sample size, the more your ability is for you to mimic the normal distribution curve. And we talked about the standard normal deviate in another lecture, in the past lecture, standard normal curve in a past lecture that just says, look, let's standardize, let's give values that you can apply to whatever normal distribution curve. And that is where we are getting the minus 1.96 to plus 1.96 and all of that, to say that majority of values will lie between 99% of values will lie between minus 2.58 to plus 2.58 standard deviation from the mean, while 95% of values will lie between 1.96 minus 1.96 to plus 1.96 standard deviations from the mean, while 68% of values will lie between minus 1 to plus 1 standard deviation from the mean. So, hypothesis testing. Basically, what it is a method for decision making. So you do your descriptive statistics, you have values, mean and standard deviations in your descriptive statistics. How does this affect or relate with population parameters? Or how is this related to two different samples? So for example, there are two ways that we look at, we apply hypothesis testing. We apply hypothesis testing to check for the difference, to check if there is a difference between the values that are derived from two comparison populations. We use hypothesis testing to check whether there's a difference. And I'm trying not to use the word statistically significant difference. When I say difference, I mean statistical difference. I'm not talking about face value difference. I'm talking about statistical difference. We use hypothesis testing in one sense to see if we can, if there's a difference between the values, the summary statistics, mean, standard deviation, the values or percentages, frequency and percentages, the values of the same variable in two different samples, comparison that you want to compare. So for example, the prevalence of women who breastfeed exclusively in urban LGs is 35%, while the prevalence of women who breastfeed exclusively in rural LGAs is 25%. At face value, it seems pretty obvious what a formerly popular politician will say. You say it is audible to the deaf and visible to the blind, that 35% is more than 25%. So you would have easily jumped to the conclusion that women who live in urban areas breastfeed more, more involved in exclusive breastfeeding than women who live in rural areas. And I will tell you, you are not likely to be correct if you do not show me a hypothesis test that you have undertaken and validated, because you are studying a sample. Do you remember that when we did this is the population. Each of these are samples, and the mean values for each sample is different, very different. So are you now going to tell me that when you get a mean of 4, you will now say, aha, it means that the mean of this population is 4. Then you take another sample, you get a mean of 5. You get confused. It means that the mean value in this population is 5. Is there any difference between 4 and 5? Is it not coming from the same population? You are not sure. And even when you are comparing, you are still not sure, because whatever difference you are seeing may really actually be due to chance and not reality. It may be due to chance and not the reality. So what do? You should be able to test your hypothesis. And they are statements. So that is in one sense, before I get ahead of myself. The second sense in which we do hypothesis testing is to try to find out the relationship or association between an exposure and an outcome of interest. Between a risk factor and an outcome of interest, an exposure or an outcome of interest. I want to find out the relationship. So, for example, what is the relationship between, so I can now say like, okay, what is the relationship between attending lectures and passing a professional exam? That's my hypothesis. What's the relationship? Remember, this is now different from there is a difference between, there is no difference between. I'm not saying what is my question, my research question is, what is the relationship between attending lectures and passing a professional exam? And so my hypothesis can be that there is no relationship between attending lectures and passing a professional exam, while the alternative, there is a relationship between attending lectures and passing a professional exam. How do I test this? I have two populations. One group of people, they attend lectures religiously. They are writing the same exam. As another group of people that read the material, go online to search, they don't attend lectures. So I want to see the percentage pass rate in these two populations, because I want to know whether there is a relationship between reading for exams, attending lectures, and passing the examination. So these are the two senses in which, the two ways we craft statements and how we apply hypothesis testing. So to be more specific, hypothesis testing, there are two different statements. We usually say, and these statements are competing statements of fact and are referred to as the null hypothesis or the alternate hypothesis. Alternate. I will correct this before. This is not alternative, it is alternate. Null hypothesis and alternate hypothesis. So the null hypothesis is designated as H0. H0. And because this is laptop, something happened. The 0 is supposed to be a small 0 under like a subscript. After the H, there's a small 0. While the alternate hypothesis is HA or H1, small a. So the null hypothesis is a precise statement, while the alternate hypothesis is a less precise competing statement. So the null hypothesis is a statement of no difference or no association, while the alternate hypothesis asserts that there is a difference or there is an association. So usually, what we want to know is there a difference? We are trying to identify differences or associations if they exist. That is what the researcher is usually going for. I want to see whether there's a relationship between attending lectures and passing exams, or a relationship between exclusive breastfeeding and the development of malnutrition in the children under 5. Whether there is a difference between the mean blood pressure of group A and the mean systolic blood pressure of group B. So in those two senses. So typical example. There's no difference between the mean weight of Ikore men and the mean weight of Kalabari men. See, same variable, weight, same summary measurement, mean. What you want to know is we saw a value. Mu1 is the mean weight of Ikore men. We got a value. And we got a different value from Kalabari men. And is there a difference? Is there a difference? So the mathematical symbols that we use is HO. Remember, the O is a small o. H0 is mu1 is equal to mu2. When you say there is no difference, it means the mean weight of Ikore men is the same as the mean weight of Kalabari men. That's what it means. The alternate hypothesis is less precise because there are so many ways you can route it. You can say there is a difference between the mean weight of Ikore men and the mean weight of Kalabari men. In this one, you're not saying which one who has more weight, higher mean weight. You just say there is a difference. So what that means is this is not 0. This is H1, please. This 0 is a mistake if you are following me. This is H1. H1 is mu1 is not equal to mu2. There's a difference. They are not the same. So it says not equal sign. H1, mu1 is not equal to mu2. Two-tailed test. What you mean by two-tailed is that it can go in either direction. You're not specific about whether one is bigger than the mean weight is more in Ikore men than in Kalabari men. You're not interested. Just let's know that there is a difference. Kalabari men may weigh more, Ikore men may weigh more. That's not what you're specifically after. Just want to identify whether there is a difference in the weight. Or you can go one-tailed upper to say the mean weight of Ikore men is greater than the mean weight of Kalabari men. That's one-tailed upper. That's the alternate hypothesis. So you see that H1 is equal to mu1 greater than mu2. It's saying the mean weight of Ikore men is greater than the mean weight of Kalabari men. Or you can go one-tailed lower to say the mean weight of Ikore men is less than the mean weight of Kalabari men. You can go lower. It's up to you. But most times in research, we would like you to go two-tailed. So really, I don't want to be seeing that you shouldn't be using one tail most times, because the truth of the matter is that you don't really know which direction it is. It is in few occasions that you really know the direction of the difference. You know there's a difference. You want to know if there's a difference, but you're not quite certain what direction that difference will take if there is indeed a difference. But you want to stick with the fact that you can identify a difference if it is higher, or a difference if it is lower, or something like that. So how do you now decide whether you will reject the null hypothesis or fail to reject the null hypothesis? Note, and this is a peculiarity with statistics, the nomenclature is never about the alternate hypothesis. The nomenclature talks only about the null hypothesis. But we know that whatever we say about the null hypothesis, you can extrapolate to the alternate hypothesis. But the tests that you are testing, the tests of significance, the tests of difference, the tests of association, focus on validating the null hypothesis. So that if the null hypothesis ends up being false, you know how to infer onto what is happening to the alternate hypothesis. If the null hypothesis ends up being true, you also know what to do to infer. Sorry about this. My slides keep jumping. Beautiful. So for you to take that decision, there are some criteria you need to use. One of them includes the hypothesis, the test of difference, or the test of, or the inferential test. And I was actually saying that we talk about rejecting the null hypothesis. You say, that means that, you remember what the null hypothesis says, that there is no difference. There's no difference in the weight of Ikwere men compared to Calabari men. There is no difference. You want to be able to establish if it is true that there is no difference, you will fail to reject the null hypothesis. Right? But if there is a difference, then you have to reject the null hypothesis. If there is a difference in the weight of Ikure men compared to Calabari men, it means the null hypothesis is not true, and you reject it. Once you reject the null hypothesis, of course, you've automatically accepted the alternate hypothesis, but nobody talks about the alternate hypothesis. Nobody talks straight about the alternate hypothesis. We always go through the null hypothesis. So, okay, I'm rejecting the null hypothesis because there is a difference between the weight of Ikure men and Calabari men. I am not going to be able to reject the null hypothesis. Somebody will say, Kuku, just accept it now. Say, I accept the null hypothesis. We don't use that terminology. We say fail to reject the null hypothesis. The reason is this, because we are being careful, because we are limited by samples. You can take two different populations now, two different groups now, similar, but maybe two different, maybe another two groups of Goni and Ikwere or something. Or you take two different samples within the Ikwere and Calabari groups. And you find out that they take, because remember, we're dealing with the central limit theory that says that if you take repeated samples, you will break through that non-normal distribution thing that you would normally have as a limitation, and most of these things will be by normal distribution if you do that. So the nomenclature we use is reject the null hypothesis or fail to reject the null hypothesis. So using the normal distribution, the normal curve, using the normal curve as our test model, you need to carry out statistical tests to be able to decide whether you will reject the null hypothesis or you will fail to reject the null hypothesis. Let me take questions before I move further.